Hindustan Institute of Technology. Department of Aeronautical Engineering. Strength of Materials. Presented by Mr. V. Ganesan. AP/Aero. Mechanical properties of materials. These describe how materials behave under different types of load. Strength, ability to withstand applied load without failure. Elasticity, regains shape after removing load, Hooke's law zone. Plasticity, permanent deformation after load removal. Ductility, ability to deform under tension, e.g., wire drawing. Brittleness, little/no plastic deformation before fracture. Toughness, energy absorbed before fracture. Hardness, resistance to indentation or scratching. Malleability, ability to deform under compression, e.g., sheet forming. These properties depend on atomic bonding, microstructure, and temperature. Deformation of materials. Definition: change in shape or size of a material due to applied load. Types. 1. Elastic deformation. Temporary, reversible. Atoms slightly displaced from equilibrium. Stress is proportional to strain, Hooke's law. 2. Plastic deformation. Permanent, irreversible. Occurs beyond yield point. Due to movement of dislocations inside the crystal. In metals, plastic deformation occurs mainly by slip and twinning. Slip. Definition: plastic deformation by sliding of planes of atoms over one another in the crystal structure. How it happens. Dislocations move along specific planes and directions. These planes are called slip planes. Directions are called slip directions. Together, slip system equals slip plane plus slip direction. Example: in FCC metals, Al, Cu, and slip is very easy because many slip systems exist. Characteristics. Produces large plastic deformation. Responsible for ductility of metals. Observed on surface as slip bands, parallel lines. Twinning. Definition: plastic deformation mechanism where a portion of the crystal takes up an orientation that is a mirror image of the original lattice across a specific plane, twin plane. How it happens. Atoms shift small amounts in a coordinated manner. No large atomic sliding like slip. Features. Produces smaller deformation compared to slip. Common at low temperatures and in HCP metals, e.g., Zn, Mg. Creates twin boundaries visible under microscope. Importance. Helps crystals reorient to activate more slip systems. Contributes to overall plasticity in metals with limited slip systems. Fracture and its type. Definition: separation of a body into two or more parts under applied stress. Occurs when stress exceeds the strength of the material. Stages leading to fracture. 1. Crack initiation. 2. Crack propagation. 3. Final fracture. Broad classification of fractures. 1. Based on plastic deformation. Ductile fracture. Brittle fracture. 2. Based on crack growth mechanism. Transgranular fracture, through grains. Intergranular fracture, along grain boundaries. Ductile fracture. Definition: failure preceded by large plastic deformation. Characteristics. Material shows necking before fracture. Absorbs large energy, tough fracture. Fracture surface, cup and cone shape. Examples: mild steel, copper, aluminum. Applications: preferred in structures because warning is given before failure. Brittle fracture. Definition: failure with little or no plastic deformation. Characteristics. Sudden and catastrophic. Fracture surface, flat, granular, perpendicular to applied stress. Crack propagates at high speed. Examples: cast iron, glass, ceramics. Danger: occurs without warning, unsafe in engineering structures. Fatigue fracture. Occurs under repeated cyclic stresses, below yield strength. Crack initiates at surface and grows slowly until sudden break. Seen in aircraft wings, turbine blades. Creep fracture. Occurs due to prolonged exposure to high temperature and stress. Time-dependent deformation rupture. Common in boilers, turbine blades, nuclear reactors. Stress corrosion cracking, SCC. Failure due to combined action of tensile stress plus corrosive environment. Example, stainless steels in chloride solution. Material testing. Purpose, to determine mechanical properties of materials for design and application. Tensile testing. Objective, determine behavior of material under uniaxial tensile load. Procedure. 1. Standard specimen is gripped in a universal testing machine, UTM. 2. Load applied gradually in tension until fracture. 3. Stress-strain curve obtained. Properties obtained. Elastic limit, yield strength. Ultimate tensile strength, UTS. Young's modulus, E. Percent elongation, ductility. Toughness. Fracture appearance. Ductile cup and cone. Brittle flat surface. Hardness testing. Objective, measure resistance of material to indentation/scratch. Types. 1. Brinell hardness test, BHN. Hardened steel/tungsten carbide ball indenter. Large impression, used for soft, medium hard metals. 2. Rockwell hardness test, HR. Cone/ball indenter, direct reading on dial. Quick and widely used. Impact test. Objective, determine toughness, ability to absorb energy under sudden load. Method. Specimen with notches struck by a pendulum hammer. Energy absorbed equals difference between initial and final swing height. Types. 1. Charpy impact test. Specimen supported at both ends, simply supported. Hammer strikes at center opposite notch. 2. ISIT impact test. Specimen clamped vertically as a cantilever. Hammer strikes above notch.